So LeetCode 1345 jump game 4. In this problem, you're given an array of integers. You are positioned at the first index of the array, and in one step, you can jump from your current index to the next one, or to the previous one, or to any index where the value in the array at that index is equal to the value at your current index. And you need to return the minimum number of steps to reach the last index of the array. So for example, here, we need to reach this index, and we are positioned here. So what we can do is we can go to the index 4 in one step because it has the same value. Then we can go to the index 3 because it is the previous index. And then from here, we can just jump here in one step. So the total amount of steps is 3. 1, 2, 3. Okay. So as you can see straight away, we're going to need some kind of map, something that keeps track of the positions where you can find some value. So for example, if I look up, okay, where can I find the value 100? That should give me 0 and 4. So let's implement that. So we're going to have just a standard map that maps every value to a set of all of the positions where you can find that value. So we're just going to loop through every index in the array, take the number at that index, check if we already have a set in positions of num. If so, then just add the new position, otherwise make a new set. Like this. So we check if you already have something, then this doesn't even get evaluated. But if you don't have anything here, so this is undefined, then a new set is made and assigned to positions of num. And then you add to positions of num the current position, right? Okay, so at the end of this snippet of code, positions is a map that maps any number in the array to the set of positions in which you can find that number. Okay, so now that we have this, we can implement a special breadth first search. It's kind of similar to a tree level order traversal. So we're going to have 2 loops and 2 queues and an outer variable that we call steps. So this is the amount of steps that we've taken, like in a level order traversal. Okay. And now we're going to also have our visited set, just like in any breadth first search. And initially the set only has the value 0. Because we start from 0, and then we're going to have our breadth first search queue, which starts with only the index 0. Right, and now comes the actual implementation of the level order traversal. So I'll just lay down the framework of a level order traversal, which is like this. So what you do is you set up a new queue that is going to be assigned to your main queue after the main queue is depleted. So basically, you have 2 loops, one outer loop and one inner loop. And the inner loop goes through and consumes and depletes the main queue, right? But you also have another queue, which is the queue that will be assigned. It's kind of like the next level, right? So this queue was the queue that you could do with steps. And the new queue is the queue that you can do with steps plus 1 steps. Okay, so like in the next iteration, you're going to have to assign this to your main queue and reinitialize it to an empty array. Does that make sense? Okay. And so the reason for which we only do this while loop while steps is less than array length, and it's not really, it's not mandatory to write this because you're going to get to the end index anyways, but I find it just makes more sense. It's because you're never going to take more than array length steps because you can just keep going to the next index, right? And so, for example, if the array length is 9, you're going to take at most like 8 steps, right? Like 1, 2, 3, 4, 5, 6, 7, 8, and so on, or 9 or something. Doesn't really matter. Okay. So that's the reason for which we have this condition here. But you could also have something like a while true, because it's going to end sometimes. Definitely. Okay. So now what you do is you take your index from your queue. So you take the first element in your queue, or the last, doesn't matter. All that matters, because like it's not a common breadth first search, so you don't have to shift the queue. You can also take from the end, because the only thing that matters is that you have your separate queue that you assign at the end. So it doesn't matter how you take the elements from your main queue, right? Okay, so we just take one element from the queue and remove it from the queue, and then check if it is the last index in the array, and if so, we can return steps minus 1. Or if this bothers you, you can also put this steps plus plus here after this while loop so that you don't have to do -1 here. Doesn't really make any difference. But anyways, so if you are at the last index in the array, then you've finished, you've found the solution. So you can just return steps -1, because remember that these are all of the indices that you can reach with steps minus 1 steps. So if you find an index which is the array length minus 1, then you've done it. Congratulations. Okay, what else? Then you just go through all of the neighbors in the neighbors of your index, and we're going to have to define this function later on, which has to follow these rules right here. And for every neighbor, you check if you've already visited it, and if you've already visited it, you don't do anything. But if it's never been visited, then you set it as visited, because you don't want to do redundant visits. You only want to visit every index once. So if it was not visited, then push it into the new queue, remember, the secondary queue, not the first queue. And yeah, that's it. So this will ensure that we never visit one element, one index more than once in our breadth first search or level order traversal. And here at the end, I've put return array.length minus 1, because in case this stops, this is like the safeguard value. So if we're taking too long, we're not finding a solution, there's definitely this solution, right? Okay, so like this is an upper bound to the number of steps that you will take. Okay, so now all that's left is to implement the neighbors function. So the neighbors function is going to have to return a list of all of the indices to which I can travel in one step from this index. So let's implement that. So we'll start with an empty result, and at the end we're going to return that result. And then what we do is we check if I plus 1 is less than the array length, then we add to our result I plus 1. Then if I minus 1 is greater or equal to 0, we add to our result I minus 1, just like the problem statement tells us. And then the other thing is we add to our result all of the positions where the value is equal. And that's why we need this map here, right? So here's where that comes into play. And yeah, here I have a fallback value. It's like a default value, which is an empty array, or it could be an empty set, whatever, just an empty something, okay? And so these are all of the indices that have the same value as this. And what you can do with that is you can add all of these to your result, because you can jump to all of these indices in one step, okay? And remember that here we're returning the list of all of the indices to which we can jump in one step. Okay, so we push to the result all of the elements in this list. And now this would already work, but there's a test case where this gives time limit exceeded. And that's because imagine if you have like a lot of values that are repeated. Like I think in the test case is a lot of 7s. So you have like 7, 7, 7, 7, maybe like 100 times. Then this would get pushed a lot of times before all of them get exhausted. So what you want to do instead is, since we're doing everything in order here, so since it's a breadth first search, like all of the next times, so for example, if we find a second time value of index, so like we use this function where index is 0, right? Let's make a concrete example. So we use this function, we ask for the neighbors of 0, and we get 100. And so we go and we see, okay, there's also 100 at position 4. So we return 0 and 4. And 0 will not be visited again because it is already visited, so this check fails. Okay, so here we find that at position 4 we have another 100. Now imagine that you had a lot of 100s in the array. Then like when you get to this one, it would be again pushing all of those 100s into a new result. And in the worst case, that could take up to n squared. So you don't want that. And since it's all in order, like once we've jumped from here to all of the other 100s in the array, it's not like when we find another 100, since we found it after this one, it's going to have a steps counter that is greater or equal to the counter that we had when we had found the first 100, right? So we're never going to find a better path from the same value ever again, right? So you could either, so what you can do to fix this problem, this O of n squared problem, is you either add to the visited set all of the positions here, or you just remove from the positions map all of the indices that you give back. And that's what I decided to do. So I take all of the indices that I'm returning, and I delete them from the set, right? And if the array is empty, it doesn't really matter because this doesn't even run once. And so yeah, that's it. I'll submit a solution to show that it works. And the time complexity is O of n, and the space complexity is O of n as well, because we just go through each element once at the most, and we just keep a queue and a visited set, and the positions map. Okay, so if you've already understood everything, you can click away. Otherwise, I'll just give you a brief overhaul of the whole algorithm, because it's a bit long. So the first thing you do is you set up a map where for every number in the array, it can return you can look up that number in the map, and it will give you a set of all of the positions in which you can find that number. Then you have your framework for a level order traversal, and the framework is an outer variable with the number of steps took so far, a visited set, just like a breadth first search, and a main queue. And you keep doing this while you are under the upper bound of steps, because you'll never take more than array length steps to get to the end, in the worst case, because you can just keep going to the next element in the array, right? And then you have your secondary queue, which is where you're going to push the next elements, the next indices that you can jump to in one step, and that gets assigned to the main queue here at the end. And then it gets reset to an empty array, and then reassigned to the main queue, and so on, right? And then you increment the amount of steps that you've took so far, and then you consume all of your main queue. So you go through all of the elements in your main queue, and you check if it is the end of the array. If so, congratulations, you found the answer, and you're sure that this answer is the shortest one because it is a level order traversal. So you visit all of the indices that you can get to in X steps before you visit all of the indices that you can reach in more than X steps, right? Does that make sense? So that's why you can just straight away return. And then what you do is, if it is not the end, then you go through all of the neighbors that you can get to, you check if they haven't been visited. If so, then you set them as visited, and you push them to the next queue, right? And so all that's left is to implement the neighbors function, which is just starting as an empty array, which you will later on return after having it updated. Then these are just the rows in the problem statement. And here you just look up into your positions map from your current value, and you have a default value of empty, of nothing. So like if there is nothing here, I mean, this won't really ever happen. I just put it there. You can remove it if you want. And then what you do is you update your result with all of the indices that you found by looking up into the map. And then you remove from the map all of those indices, because once you've used them once, there is no point in using them again. That would just lead to an O of n squared time complexity in the worst case, and it doesn't help you, because all of the next times are going to have, at best, the same amount of steps. At worst, they're going to have more steps even. So there's no point in keeping these positions that you've already used. It's basically like you can get them, you can think of these positions as being already visited once you return them once. And so what we do is we delete them from the map. Or if you want to, if you prefer, you can add them to the visit set as you want. So that's it from me today. Thank you for watching, and bye.